stick around if you don't want to. Whatever you want afterwards. But you're welcome to stay and we'll do a little bit of club business and stuff and then go off some scopes and stuff. But anyway, without any further ado, to start everything out here, are you ready, Scott?
Yeah, yeah, it's streaming.
Yeah. Okay. All right, streaming. Hey. So, welcome to the November meeting of the Baton Rouge Astronomical Society. As you can see, somehow you got stuck with me up here once again. I wasn't here last month, and Don finally returned, and now Don is up in, I believe he said, Tennessee. Seems strange because John's up in Tennessee also doing something different, John is. But yeah, Don is doing some vacation stuff away, but he should be back next month. Of course, he'll be back next month if we have food.
Yeah, fish and that too.
Yeah. After the presentation, we'll take a short break, have some wonderful cupcakes and cookies over there and whatnot, and we'll do our normal club business, and then hopefully get outside and do some observing in the freezing cold. But without further ado, please welcome Mr. Eric Borowski from LSU's Department of Physics and Astronomy. Take it away, sir.
Hey everybody, good to see you. Don't miss out on the Confi or spectacular. But like Ben said, I'm Eric Borowski. I'm a graduate student at LSU. I study black holes in systems called X-ray binaries. We'll get into what that breaks down to in a little bit here. But today I want to talk to you about how astronomers find black holes, and then a little bit about how some astronomers, myself included, study a subset of black holes. So let's start with the overview of fantastic black holes and how one might find them. So before we talk about finding a black hole, we should probably all be on the same page about what they are. So what are black holes, right? And the definition we're going to adopt for today's purposes is if you pack enough mass into a small enough volume, a resulting gravitational field exists from which nothing can escape, not even light, which is the fastest thing in the universe, right? And so you've probably seen some depictions like this, where you have space-time represented as this two-dimensional, the stretched out sheet that when you place a mass into it, it distorts that grid, that sheet. It leaves an indentation in it, and that distortion is a representation of a gravitational field in space-time, right? So a smaller mass will leave a smaller divot, which implies a lower gravitational force, right? Than a larger mass, or an even larger mass, right? Which will distort more and more. And so as you get to higher concentrations of mass packed into smaller volumes, that distortion effect becomes much more pronounced, right? So the sun maybe leaves sort of this kind of shape in the sheet. A white dwarf, which is the dense core of a star that our own sun will eventually, billions of years from now, meet its fate as a white dwarf. And then like really, really large masses packed into really, really small areas can make particularly distorted spacetimes, right? So neutron stars, the second most dense matter in the universe, will have a really dramatic effect where you can start to see some general relativistic effects in their vicinity. And then the most dense concentrations of matter in the universe, which we refer to as black holes, anything that passes within a certain radius of that mass will fall in and never escape, right, including light. So you might think about making your own black hole. This is one of two equations. I promise I won't bore you with a bunch of math. But say you wanted to create your own black hole, you could perhaps cram in kilograms worth of stuff into a sphere with this radius defined by this equation. So this is a Schwarzschild radius, and in the simplest case of a non-spinning stationary black hole, it describes the distance from the city to the event horizon, that point of no return around the black hole, right? And so it's a relatively simple calculation. So it has g, which is a Newton's gravitational constant. It has c down here in the denominator, that's the speed of light. And then the only thing that changes, the only thing it depends on, is the mass of the black hole, right? So you can talk about the size of the black hole and spatial extent just with the mass. Again, in the most simple case of a very plain, non-rotating black hole. So say you wanted to do this. Turns out a black hole with the same mass as Earth, just something like 6 trillion kilograms, or if you like scientific notation, 6 times 10 to the 24 kilograms, would have an event horizon less than 2 centimeters across. So that's kind of not a physical picture, right? We don't see black holes this small, at least we haven't yet. But it gives you an idea of kind of the extreme nature of these objects, right? So the entirety of Earth's mass crammed into a volume 700 million times smaller. Sorry, a sphere with a diameter 700 million times smaller than the Earth. Okay, so not super practical. Maybe we'll just go look for them elsewhere rather than trying to make our own. So as I said, we can describe most properties of black holes, including their size, with their mass, how much mass they have. And usually we describe them with a scale relative to the sun. So it's 3 solar masses or 3 times the mass of the sun, right, for example. And so the natural sort of classification scheme then is to break them up, the black holes we observe, by their masses. And so at the lower end of the range, where you have black holes that are a few times to perhaps 100 times the mass of the sun, we call these stellar mass black holes, because they're comparable to the masses of the stars we see in the universe. On the other end of the spectrum, we have what we call supermassive black holes. These we observe at the nucleus, at the core of every massive galaxy. We think they're ubiquitous. And so they range anywhere from several 100,000 times the mass of the sun to millions and even billions of times the mass of the sun. So that's a pretty big gap between stellar mass and supermassive. It turns out that this range in between, there's not a whole lot of observations of black holes that bridge that gap of masses. So we call them intermediate mass black holes, but they're kind of just a question mark. And in fact, every day we find larger and larger stellar mass black holes with LIGO, which shrinks the range from that side. And then, of course, people are always looking for smaller supermassive black holes. And there's a few suggestions that people may have found a few of these that fit right in the middle here. But the observations are few and far between. Anyway, so that's how we'll talk about black holes and categorize them. So let's talk about where each of these classes come from. Yeah. So stellar mass black holes, we'll start at the lower mass end of the spectrum. These come from the deaths of the most massive stars we see in the universe. So stars that are more than 20 times the mass of our own sun. These will eventually end their lives in a stellar mass black hole. So in the end of life of a really, really massive star, in this case 25 solar masses for the descriptions here, stars all fuse elements, lighter elements up into heavier elements in their cores. Right, this is powered by the gravitational force, which brings all this closer together. Most stars spend most of their time fusing the lightest element, hydrogen, into the second lightest element, helium. But if you have more and more mass, there's more and more gravitational force in the center of the star, and you can start to fuse up heavier and heavier elements. And in the most massive stars, you can go all the way to iron, which is sort of the dead end of stellar nucleosynthesis. So there's some sort of complicated physics reasons why, but for our purposes, let's just take it as fact. As you go, maybe 10 million years burning hydrogen to helium, you might burn helium into carbon for a million years, carbon to oxygen for 600 years. We look for stars that are burning carbon to get an idea of stars which might soon go supernova, by the way, and explode in the universe. Oxygen to silicon burning only lasts 6 months, and the last stage, turning silicon into iron, lasts for only about a day. After a day, there's so much iron built up in the core that the force of gravity is stronger than the forces holding up the core of iron, and the core collapses. And that takes about a quarter of a second and releases tremendous amounts of energy. So these are supernova explosions. They come in various flavors and have different interactions. But in the case of a most massive star, when it goes supernova, the core that's left is big enough that it collapses directly to a black hole. You can also sneak in, sneak around this sort of mass limit if you have a star that's maybe 10 times the mass of the sun. When it goes supernova at the end of its life, it can result in a neutron star. That's, again, as I said, the second most dense thing in the universe. And if you just add enough stuff to a neutron star, it too will collapse into a black hole. So you had to get it from underneath to over about 3 times the mass of the sun. The uncertainty there is still an active area of research. So while I take a sip of water, we'll look at a nice fun animation of a supernova because it's really neat. So you might see a star get really big and really bright in the sky. It's been a while since we've had one of these happen in our local neighborhood. We're anxiously awaiting another to see what we can learn about the end of life of stars. But at the center there, the most massive star, you have a black hole left behind. So what about the other types of black holes? Ones that I mentioned and others. So supermassive black holes that I talked about, right? We think these ones that are hundreds of thousands to millions of times to billions of times the mass of the sun probably started as initial seed black holes, maybe in the range of a few hundreds to a few thousands of times the mass of the sun, which grew up gradually over the lifetime of the universe by absorbing material, which we call accretion, or by merging with other black holes that they found along the way, right? So you take 2 1,000 mass black holes, they spiral in, they merge together, you get a 2,000-ish mass black hole that comes out. And so we think that's how those supermassive black holes probably formed, with repeated mergers over and over. Sorry, I should say, if you have questions at any point, please just put up your hand and I'll call on you, and we don't have to listen to me ramble on the whole time. Yeah, what's up?
Can you just explain a little bit what a seed black hole is?
Oh yeah, so I just mean one that's smaller than the supermassive black hole we see today, right? Just that adds mass. It's not a technical term.
Did it come from a star explosion?
Or
just dust accreting in the universe?
Probably both. Probably both. So the earliest stars in the universe were probably entirely hydrogen, right? Before we had fused up a bunch of elements into other things, and those could have gotten really, really big. This is theoretical. And when they would have collapsed, they would have left behind really large black holes.
So that was a star.
That's one way. That's one way.
Is there any guesstimate of how much of what fraction of the total mass of the universe is already collapsed matter?
It's a great question. I definitely don't know off the top of my head, but supermassive black holes make up a significant percentage of the mass of the galaxies. And so if we just sort of extrapolate out from there, right, we're talking, maybe as much as
time function, right?
Sure. Maybe as much as 10%. And that is, super. Don't quote me on that. We can research it later if we want the real answer. But yeah, another.
Is accretion like the general theory of black holes? Do people think that black holes can do accretion?
Definitely, yeah. So that's how I study black holes, and we will get to the details of that a little bit later. Okay, so maybe you can also form black holes, including supermassive black holes, by direct collapse of large amounts of gas, right? And so depending on whose theory you believe in and the conditions you think this large amount of gas started with, you could maybe make a black hole between 100,000 and 1,000,000 times the mass of the sun through this direct collapse of gas, skipping ever forming a star. You could also, perhaps, and these are things that that we're very interested in, but still elude us, could have primordial black holes, which would have arisen from quantum fluctuations in the very early universe, like in the first moments after the Big Bang. And again, depending on whose theory you believe the most, they could range anywhere from 1/100,000th of a gram when they formed, and they would have evaporated quite quickly at that mass, up to maybe 100,000 times the mass of the sun. Yes.
In a direct collapse event.
Uh-huh.
Even a trace.
So we've never observed one. It'd be hard to say. I think probably you would end up with some amount of accretion that went on after the direct collapse, which would emit light. But again, no one's certainly never observed one of these. Okay, so now we are on the same page about what black holes are, how we describe them, maybe where some of them come from. Let's talk about ways that astronomers can find black holes, right? And I think for Louisiana, and well, for modern astrophysics, the most relevant and fruitful way is by searching for gravitational waves. So gravitational waves are literal ripples in the fabric of space-time that come from the acceleration of massive objects. And so if you get large enough, like massive enough objects accelerating in space-time, right, and perhaps they're orbiting each other as they spiral inwards towards a merger, you can detect the ripples that those gravitational waves generate with really, really sensitive measuring devices. So the reason I say it's extremely relevant for Louisiana, as most of you probably know, but I'm going to pretend someone here doesn't so I can talk about it. We have LIGO in Livingston, which stands for the Laser Interferometer Gravitational Wave Observatory. And so you can think of this device and its sister site in Hanford, Washington, as the most sensitive measuring devices ever built. They can measure, so they have these really long arms that go out 90 degrees from each other, this L shape, both of them have this feature. Each of these arms is 4 kilometers long, and they set up a measuring device such that they can measure the change in length of one of these 4 kilometers arms by 1/1000th the width of a proton. That's like measuring the distance from where I'm standing to the sun with the accuracy of the width of a human hair. It's a really profound feat of engineering that we're able to do anything like this. And so I'll show a short animation here of what this looks like kind of in real time, right? So we have 2 black holes. They're spiraling around each other. They've been doing this for a very long time. This is the final moments of their lives as individual black holes before they in-spiral and merge into one larger black hole. And so you'll see them spiral inwards, merge together into one black hole, and then they ring down kind of like a bell. So here's a sort of schematic view. These green waves are gravitational waves, right? They're ripples in space-time, actual shortenings and lengthenings of space itself. When that merger happens, those gravitational waves get higher in frequency and larger in amplitude. They propagate outward through the universe, where we detect them on Earth. There's a vastly exaggerated effect, as they say here, but literally the Earth itself shrinks and lengthens by, again, fractions of the width of a proton. But we can use laser interferometry to detect the changes in length of the arms by the signal that the mixed lasers produce on a detector. Right, so they go down the arm, they bounce back, we recombine them. If the length of one of these arms changes, you get a brightening and darkening, which is recorded on the detector, and you can infer the existence of merging black holes. And so this is by far the best way to find black holes. In the 10 years since 2015, which is the first merger of black holes that we detected with LIGO, we've seen all of these through gravitational wave events, plus some. This is a slightly out of date figure. But so the way to read this, right, is there's a mass scale on the side, again, in units of the mass of the sun. You have, I don't know if I can hold this steady enough. You have one black hole here that's maybe, 11 times the mass of the sun. One black hole here that's maybe 50 times the mass of the sun. They merge into something that's about 60 times the mass of the sun. So, in a sense, by finding all that led into it. And so we found, depending on how you look at it, all of these black holes with gravitational wave effects. So like I said, if you're just looking for sheer numbers, it's the best way to do it. To compare, these are the black holes we found before we had gravitational wave detectors. And we'll get into a little bit about how you might be able to do that. Yes?
Do you have any idea on that scale which one was the first?
The first one was pretty large. I think it's one of these guys. Yeah.
It was multiple times.
There seems to be a very much of a parity of the partners.
In terms of, you're saying they're similar masses?
Yeah, they have similar-ish mass in the marriage, I guess. There's something there. There's
Why might that be?
Yeah.
So the first thing that comes to mind is there's probably some amount of a selection effect. Higher mass ratio mergers are a little bit more difficult to detect. So when you end up with two that are quite similar masses, I think maybe you just get a better signal.
Smaller ones just drop out as noise.
There may be something phenomenological about it too, that I just don't have the theory on. Yes?
So, if I remember right, when LIGO was first made, they didn't detect anything for several years, right?
Yeah, I think they turned on the first time in maybe 2010 or something. Maybe even 2005.
So all these have been detected, since then, since 2015?
Yeah, that's right. Yeah, 2015 was the first detection.
Why are there so many in the past 10 years and then none in the previous 10 years?
It's entirely the sensitivity of the detector getting better. So a lot of engineering work went into optimizing the detection rates. So they isolated seismic noise, thermal noise. They've got very special coatings on the mirrors that make the beams back very coherently. And so it's completely a matter of detector sensitivity.
Yeah, there was LIGO, and I remember we even had Dr. Gonzalez, Gabriel Gonzalez came out, and I remember her giving us a talk, and, updating us how, they had a null result, they hadn't detected anything and stuff, and then, they shut it down and redid all of this, upgraded all this stuff, and I believe they called it advanced LIGO after that, and as soon as they turned it on, they started making that.
Oh, wow.
It just made more sense.
Yep.
So, gravitational waves are one way, perhaps the best way, depending on your bias, for how to find black holes. But how else might we be able to do that? So, light. Light is a great way to find black holes. And you would be right to be a little bit skeptical of that statement, since I told you that if light passes within a certain distance of a black hole, it falls in, never to return. And the primary way we see things that aren't emitting their own light is to see the light reflected off of them. So it would be fair, and you should hold me to account, if I told you that the next best way to find black holes is with light. But there's a few really clever techniques that we demonstrated to do this. So the first one I want to talk about is indeed gravitational lensing. So this is another effect, another phenomenon described by Einstein's general relativity. This and gravitational waves both come from Einstein's theory of general relativity. This one, again, has to do with the distortions of space-time made by mass, in particular really dense collections of matter. And essentially what you get is the light, which is traveling through space, has to follow the path of the distortion if it comes through it on its way to us. And what that can end up looking like is a star which we observe. We would have, if the black hole wasn't there, it would have looked just like this to us. Hole. The light takes a different path, and in fact is amplified, magnified, so that we see a brighter and a shifted star compared to its actual position, right? And so this is, I think, one of the cooler ways that you might find a black hole, but it's not been super fruitful thus far. Here's a nice sort of cartoon animation of the way a passing foreground black hole might distort the light from galaxies behind it. You can see, right, like as it passes in front of this one, we get a lot more light right about here, right? That's that bump in magnification, and it's shifted slightly, right? This happens with individual stars too. So we think we have seen this happen. There's another pretty recent, decent case for this. But Hubble Space Telescope was able to observe what we think is a gravitational lensing event. So this star right here got way, way brighter in 2011 and then decayed in brightness, right? The reason we knew to look at it is because it suddenly got really bright. And actually, if you do really sophisticated analysis and measurement techniques, it shifted position slightly as well. And so a really large mass would have had to be in between us and that star to make such a dramatic effect. And there's nothing to be seen, right? And so you can infer something that large, which emits no light, must be a black hole, right? And so this is a way you might find black holes with light, gravitational lens. So another way, this is a section equation, and I promise not to drag on too much as I talk about it, but another way we can use light to discover black holes is actually kind of like, we can use the light from a star, which is gravitationally influenced by a black hole, to infer its existence, right? So we can tell about the orbit of an object if we get nice enough measurements and we use Johannes Kepler's really nice formulation of the his third law. We can massage it into a form where we can use things like the period of the orbit, the velocity of it as it moves through its orbit. We can sort of relate it to like what angle this orbital plane is with respect to our line of sight. It's I'm not saying it's easy, it's a little bit complicated, but you can definitely get to eventually the mass of one of the objects and the ratio of the mass of the two objects, which then leaves you with the mass of the one you can't see, right? So it's a bit of a tricky way, but a clever way to do this, and we have in fact done this. So I think the best sort of visual demonstration of this is looking towards the center of our galaxy. We've got to look through a lot of dust to do this, so it's not entirely uncomplicated. But you can watch these stars sling around something really, really big right in the center, right? And extremely close approaches. And so we can look at the orbit, the size of the orbit and the velocity that that thing has, get an estimate of its mass from like sort of the regular astronomical techniques you might use to weigh a star, and then infer the mass of that unseen object to be a supermassive black hole, right? This is a more schematic. Was there a question? So good question. This one, watch this one. It's got a timestamp down at the bottom here. So this is a more schematic view, right? It's got these trails traced. This is in radio wavelengths, again, to look through the dust. And it's also the reason you can see something here. This is hot gas around the supermassive black hole at the center of the galaxy, which is labeled SGR 8 star. That's Sagittarius 8 star. That's what we call the Milky Way supermassive black hole. Anyway, you can see these things coming within about the distance that Neptune comes from the sun of something way, way more massive than the sun, hundreds of thousands of times the mass of the sun. And so you can trace this motion out. You can get an idea, okay, what is this orbit like, and what's the velocity along this part of the orbit, and you can get an idea of what the mass is like. So,
It's Holland.
Yeah, and this, yeah, on its closest approach here, yeah.
Then you're going something like 100,000 miles.
Sorry, what's that, Scott?
They're really.
Yeah,
You're not going going around 100,000 miles a second. You're not going a significant fraction of the speed of light.
certainly, certainly. I don't even have an order of magnitude guess for that, but it's real fast. So there's another trickier way to see the orbits of things that you can't actually see move along the plane of the sky. As a bright object approaches or recedes from you, right, travels directly away or directly towards you in an orbit which you otherwise can't measure, you can look at the spectrum of that star, right, the colors of light that it emits. You can break up the light of the star with like a prism, and you can look at that rainbow, and there's usually distinct features, absorption or emission lines, that you can identify and watch them shift blueward or redward. This is red or blue shift, for those of you who are familiar. As the object's as the object's orbital motion is directly away or towards you. So the faster it's moving away from you, the more red shifted it is. The faster it's moving towards you, the more blue shifted it is. So you can look at this, and what it would otherwise just be a dot in the sky, you can look at how its spectrum shifts. You can tell how fast it's moving. You can get an estimate of its mass, and then infer the mass of the thing that is orbiting, right? And so you can do this. This actually is an example for exoplanets, where they use radial velocities quite often to measure, to detect and to measure exoplanets. But you can do this with black holes as well. So the last way I want to talk to you about finding black holes is accretion and outflow. So this is my personal favorite. I'm a little bit biased. Accretion, as I mentioned, is the adding of material to a black hole, absorbing matter over time. And then outflows are a little more complicated than that, but it is what it says. It's things flowing away from the black hole, right? And so you have this in the case of supermassive black holes, and the sensors of galaxies, which accrete from giant reservoirs of gas in the central regions of the galaxy. And you also have this for stellar mass black holes, which can absorb material donated by a nearby companion star that they're locked into an orbit with. So those ones, the stellar mass black holes that absorb material from a donor star, are called X-ray binders. So those are the ones I study, and we'll perhaps have a little bit of time to talk about how I study them. I don't know where I'm at, but we'll save that for a minute. But so the different components you have, right? As I said, you've got the inflows, the accretion. That's so this accretion stream, the material siphoning off of the star, because it has angular momentum. Instead of falling directly into the black hole, it spirals around, and that material is transferred and spirals and transferred and spirals, and it builds up into what we call an accretion disk, right? So a disk of material around the black hole, which slowly gets absorbed over time. You can also drive winds off the disk. You have really, really bright, energetic light generated towards the center of the black hole, towards the center of the accretion disk where the black hole is. That can propel material off of the disk in the form of winds. And you can also form these jets from the poles of the black hole. These are a little bit more complicated. Their formation mechanism is less well understood. Suffice it to say, it's general relativistic magnetohydrodynamics is one of the theories that describes how you can get some of this material from the disk, instead of falling in, to be slung off at the poles in the form of a jet moving significant fractions of the speed of light. So to summarize, astronomers find black holes through the gravitational waves, the ripples in space-time they make when they merge, gravitational lensing, right? The way light travels differently along the distortions in space-time that black holes make. By orbital mechanics, right? That's observing the motion of things you can see as they dance with the black hole. And then when black holes interact with matter in the forms of accretion and outflow, you can catch them then too. So if you are really clever, perhaps someday soon you can come up with a new way for astronomers to find fantastic black holes. So that's part one of the talk. Let me see how much time I have. Because I had 2 minutes of this, a 20-minute version and a 1-hour version. So maybe we can just touch on, this was the 20-minute version, by the way. It went 35 minutes. So, but we'll talk a little bit about how we might study black holes, specifically myself. And I'll keep this, it won't be another 35 minutes. So, as I said, I like to study accreting black holes, in particular the accreting stellar mass black holes, which we call X-ray binaries, primarily because the method of discovering them is through X-ray telescopes. Right? That was the first way we found these things. So, similar accreting black holes happen in active galactic nuclei, right? That's the supermassive black holes at the center of galaxies, and in collapsars, right? Those stars that are massive enough to collapse directly to a black hole at the end of their lives. All these three seemingly distinct astrophysical objects are all fundamentally an accreting black hole, right? The physics is the same. Their energies are different. They're scaled in different ways. The size scales are different based on the mass of the black hole. But so, like, for example, in the case of a stellar mass black hole, you might have a jet that spans light years. For a blazar, that is an active galactic nucleus, a supermassive black hole at the center of a galaxy, it might have jets that span millions of light years or more. And these collapsars, these things that, when a stellar mass black hole is formed at the end of the life of a star, are really quick, bright events, also known as gamma ray bursts. And these things are much more compact, and the energy densities are much higher, right? But essentially, they're all still the same accretion and outflow, right? It's all accretion and outflow. What can we get from that? And it turns out this is the best way to study regions of space-time that are the closest to a black hole. So, as I said, X-ray binaries were discovered primarily from X-rays that we detected in space. In fact, they're the first type of astrophysical transient, right, a quick bright event that we captured with space-based detectors, right? It didn't happen until the 60s when we sent X-ray detectors up on sounding rockets out into the atmosphere, and suddenly no one really expected to see a whole bunch of bright X-ray sources in the sky, but all of a sudden there were a bunch, and they were really bright. And so the search was quickly on to find out how you could make something like this. So we mostly see X-ray binaries in the plane of the galaxy, right? So not sort of extragalactic. We see a few out there, but distances are pretty vast. Not really in the halo of the galaxy, but mostly in the disk, right? So this is galactic, a projection of the entire sky in galactic coordinates. So this line in the center is the disk. This is far above the disk. This is far below the disk. This is one of our first maps of X-ray sources in the sky. This is the first one we found. That's Scorpius X1, the really bright neutron star, actually. But these are a collection of X-ray binaries that we found. So we've gotten a lot better at this in the preceding years, and this is what the X-ray sky looks like now. This is from E Rosita, a satellite launched in 2019. You can still see SCO X1, but you can also see some really cool features, right? There's a bunch of bright dots. Those are point sources. Those are X-ray binaries. But you can also see a bunch of diffuse emission from hot gas in the galaxy, and these really interesting bubble-shaped things, which suggest that maybe at one point in the past, the supermassive black hole at the center of our galaxy was actively accreting, and the jets blew out these large bubbles of material. This has been a very long time ago, and we're quite lucky that it's not still going on. So, I'll wrap up really quick after this. But so black hole X-ray binaries, right? So stellar mass black holes accreting material from a donor star come in two main flavors. You have high mass, which refers to the mass of the star that's donating material, and low mass. Low mass X-ray binaries are the best. Those are the ones I study. But so in the case of the high mass, it's mostly stellar winds blown off, just as a normal part of high mass stars' lives that fall onto the compact object, the black hole. And in low mass X-ray binaries, you actually get this phenomenon called Roche lobe overflow. And I won't belabor the point too much, but essentially the star gets distorted in this teardrop shape, and some material crosses over this point where the gravitational attraction of the black hole is larger than the gravitational attraction of the star, and so material is siphoned off, and it forms that distant problem. Anyway, like I said, low mass X-ray binaries are the best, because those are my favorite. I've got some backup slides we could probably talk some more about, but that wrap up the formal talk right there. So that's it. Thanks. Yeah, well, no good X-ray binary talk leaves out an image from Dr. Borowski, the Vincent. Anyway. Okay, any questions for me?
Yeah, how soon is the interview going
Anywhere between tonight and 100,000 years from now.
Well, it has to go at least 540 years ago for me to see that.
Well, we're talking about when the light from the explosion reaches us. Well, I guess it also depends on when you think the supernova starts, right? Is it shock breakout? Is it the core collapse, when the iron core collapses and neutronizes, right? I mean, there's lots of things you could quibble over here, but
When did the explosion happen?
between tonight and 100,000 years
Yeah,
from
but like, in what part? Is it when the iron core collapses?
Yes, yeah. So the very end of life is it can't fuse iron up into heavier elements without an injection of energy from elsewhere. So that iron core just builds up until it's too big to hold itself up against its own gravity, and that collapse happens.
Supporting pressure disappears.
That's the supernova. Yes. Oh, thank you. I appreciate that.
I'm probably totally misunderstanding the physics, but wouldn't the gravitational waves also get sucked into the black hole?
So, interesting thought. So I think
They're outside of the event horizon.
you can think of it, yeah, so
They have no mass.
there's something to that, right? You're right. There's no mass, right? But certainly we have, I mean, so you can think of, right, ripples in a pond interacting with each other as they propagate outwards, right? If you have two stones dropped in a pond at different places, right? They do interact in some way, but gravitational waves travel at the speed of light, and they're actually, I mean, they're not, it's not like electromagnetic radiation. It's actual changes in like the unitary length of space and time. So like physically reality stretches and shrinks, and that propagates outwards.
So is it light?
Gravitational waves?
Are they considered light?
No, they're ripples. They're closer to sound waves than they are light waves. But we detect them by using lasers. So I guess maybe it's all light. I don't know. Yes.
Back where you talked about the stars and 10 million years fusing and so on, and the time periods and whatnot. You said that we look for carbon burning stars, but the next one down was 6 months. The silicone burning have we seen any of those? And then like, oh, okay, something really just about that.
I don't think so. So that's such a brief moment of time in the life of a star that there's not going to be, at any given time in the universe, a ton of stars that are currently burning silicon. But also the spectral signatures, right? You need to dredge some of that up to the surface of the star to see the spectral fingerprints of that kind of burning, right? So I think probably, I mean,
How would you know?
the ends of lives of stars can be really, really dramatic and violent, and you probably do have dredging episodes that can bring some of that stuff up. So the chance of us catching that quick enough, one, it being close enough that the signal's strong enough, we just happen to get a spectrum of it. I mean, better to wait the 6 months until it's one of the brightest things in the sky.
When was the last one?
So the Milky Way proper has been hundreds of years, but in the Large Magellanic Cloud, there was a supernova in 1987, which is, I mean, the Magellanic Cloud is a dwarf galaxy that's just orbiting our own, eventually to merge in with the rest of it. But that was supernova 1987A. That's the last nearby.
I just saw that recently there was a star that we actually had images and measurements of before it was supernova in a neighboring galaxy. I can't remember the details, but it very, very recently.
Sure, I seem to remember something like this too. I mean, it's extragalactic, but yeah, there was like a blue supergiant star, and then it was a supernova, and now there's nothing. Right. At least nothing visible to us from this far away. Yeah, that I do recall seeing something about that.
So were this, like I know James Webb, aren't they saying now there's galaxies that are bigger than they even thought earlier? So what happened first? Black holes or stars in the evolution? Because now I didn't really realize that black holes can just come from the dust itself. So what would be formed first? The stars, and then they go into black holes at the beginning of the universe?
It's a great question. So if primordial black holes were formed from quantum fluctuations in the first moments of the universe, then the black hole would be first. Otherwise, I think you need a generation of stars, or perhaps direct collapse of dust.
So what's the evidence really leaning towards?
Well, I mean, the amount of mass in the universe that can be primordial black holes, based on the observations we've made, gets smaller and smaller, right? Like, if there are primordial black holes, there can't be that many of them, right? We've seen them by now. So I think primordial black holes are getting less likely.
Stars forming first.
And direct collapse is definitely something that's a bit of a gray area. So I think if I had to put money on it, I'd say the first generation of stars probably made the first generation of black holes. Please.
You go to one of your slides where you had like the space time grid.
Yeah, sure.
That's gonna be kind of a question.
I'll look back.
Yeah. So, I mean, we have our little gravity well, too, a little stretching back there.
Mhm.
And whatnot. So, it's like this area here, that's the
That thing on fire.
what do they call it, the event horizon, I guess, out there, right? I suppose that, like, make a circle around that black hole there.
Well, so that would be just this is a compact object that's less dense than a black
It
hole.
doesn't have.
Okay.
A black
Yeah.
hole has a mathematical singularity, and so what you would see in the sheet is this infinite curvature, where you never actually have a bottom.
I guess my real question is, like, with this model here, is that where the gravitational pull of that object ends? Like, is it flat after that? Or, like in our little simulator,
Sure.
You see the curve, but where,
Well, it goes actually
So-
to the zero.
Yeah.
and hyperbolic curve.
yeah.
So it's not flat, it's just
Yeah.
hyperbolic curve.
But like space time, is it flat and then something's there, but just for a little bit, or upper limit?
No, so our theories of gravity say that it extends out infinitely. I mean, it gets way, way, way weaker as you go out distances from the mass, but technically there's a small gravitational attraction between us and the first galaxies. I mean, it's so negligible as to be almost not worth mentioning, except for the Lindsay it inspires it.
And you said the 1.8 centimeters, right?
Yeah.
What was 1.8 is what? The Earth would make?
The diameter of
That right there, the
the-
diameter of what?
of the event horizon.
The event
So-
horizon.
The region from which its light passed within, it cannot escape, which you can kind of think about as the physical side.
So our massive black hole in the center of the Milky Way is light years across. If the Earth is 1.8
Not light years. It's surprisingly small still. So
Just
you
as a
gotta put me on the
comparison
spot.
to Earth.
Okay, so one, it's spinning, right? All black holes are spinning. That's a secret I didn't tell you when I described this really simplistic equation, right? But if you put, 500,000 here, this is 6.6 times 10 to the minus 11. This is 3 times 10 to the 8. Someone's got a calculator or really good at math in their head. You can work that out yourself. But yeah, it's quite small still. It's quite small. So like the
I think it would be, the black hole itself has no physical dimensions. It's essentially a point, there's no singularity.
But I was just going to compare the Earth to the 1.8
What they're doing
centimeters.
is the event horizon mathematics.
the question
The
is,
actual black hole has no physical dimensions.
Right, but that was the 1.8 centimeters, right, was the
Yeah,
event horizon?
correct, you're
I
right.
just wanted to go home and tell my husband, look what the Earth would do and look how such a large comparison.
No, yeah. So I bet you if you type this into Google, it would
Oh, yeah.
solve it immediately.
What dictates the orientation of
Good question. It's primarily the orbital, the same plane as the orbital motion of the star around the disk, or right, the gas around the disk is this. I mean, I guess I see the contingent you might have here. At least in the case of X-ray binaries, it's the plane of the orbital motion. So the where the star is that's donating the material, the plane that it revolves in, that's the same plane as the disk. In the case of the galaxies, I guess it's it's the same concept, but you have a lot more mass distributed over a lot larger areas, but it's still in the same plane as the
I guess all
rotation of the
most solar
galaxy.
systems are about the same plane as the plane of the galaxy.
Sorry, what was that?
Or are most solar systems the same plane as the plane of the galaxy?
No, I think they're mostly evenly distributed across all angles.
Okay, so it just
but
it happens.
Bulk motion of the stars around the center of the galaxy is one plane mostly, right? That's what makes the disk of a spiral galaxy. There is one fun tweak to that, right? Is that I said these black holes have spin themselves, right? And sometimes their spins are misaligned with the axis of the disk, and they can make like weird humps in the inner regions of the disk. So it's orbital plane all the way down to the inner regions, and then it gets really funky around a rotating black hole.
So it is what it is when it started, and it started in that direction.
Yep.
Now it-
Yep. The axis of rotation of our Milky Way's supermassive black hole? I don't know. I don't know that we have a great, if we could see the jets coming out of the poles, we'd have a great notion of that, but I think it's a bit harder to measure.
I seem to remember there was talk about it when they were first taking those images.
The Event Horizon Telescope. Okay. All right. Thanks for listening.
Quite excellent, thank you very much.
How much of the raffle tickets are pocket?
Yeah.
Although, from what I understand, Chris is building a small altar to these rockets.
Let's just take just a couple of minutes, say 5, less than 10 minutes, and take a little break, socialize a little bit. If you have any other questions you didn't want to ask in front of the group, come ask Mr. Eric here, and then we'll reconvene in just a few minutes and do just a little bit of club business, and then we'll get to some observing.